Hello and welcome back. The last video I talked about chemical reactions of haloalkanes, and as I had promised, in this video we'll be looking at stereochemical aspects of nucleophilic substitution reactions. Before jumping on to stereochemistry, I would like to highlight two important points that will be the end result of this video. You may not understand it for now, but just remember this. A SN2 reaction proceeds with complete stereochemical inversion, as I had said in the last video. We will look into these terms in detail in this video, and by the end of this video you will be able to understand what these words mean. And this I didn't mention in the last video, but a SN1 reaction proceeds with racemization. So in order to understand this concept, we'll have to learn some basic stereochemical principles and notations. Let's go on. Certain compounds rotate plane polarized light. What's a plane polarized light in first place? You might have seen in physics that a light is electromagnetic radiation. It has vibrations in different directions. A light is said to be plane polarized if these vibrations of light can be restricted to a single plane. You will be learning this in great detail in physics in a chapter called optics, but I hope you have got an intuition of what plane polarized light means. It's simply a light in which the vibrations are restricted in a single plane, just like restricting the vibrations of a string in a single direction, say up and down. So yeah, let's move on. So certain compounds rotate the plane polarized light produced by passing ordinary light to a nickel prism when it is passed through their solutions. Such compounds are said to be optically active compounds. Nickel prisms are special instruments used for producing this plane polarized light. So such compounds are called optically active compounds. The angle by which the plane polarized light is rotated by such optically active compounds is measured by an instrument called polarimeter. If the compound rotates the plane polarized light to the right, that is in clockwise direction, it is called dextrorotatory, and we represent it by D form, and it is indicated by placing a positive sign before the degree of rotation. For example, we say that this compound has rotated the light by plus 5 degrees or plus 10 degree. If the light is rotated towards left, which is anti-clockwise direction, the compound is said to be levorotatory or L form, and a negative sign is placed before the degree of rotation, for example minus 5. And note that D and L are in small letters. The capital D and capital L means something different, which we will not be looking for now. So we are using small d and small l for denoting dextrorotatory and levorotatory, and plus and minus signs respectively. Such plus and minus isomers of a compound are called optical isomers, and the phenomena is termed as optical isomerism. So what's a stereocenter? It's a new term. Let's look at it. The spatial arrangement of four groups around a central carbon is tetrahedral. We all know this. We have learned this in class 9th, I suppose. And if all the substituents attached to that carbon are different, such a carbon is called asymmetric carbon or stereocenter. So what's the stereocenter? If we have a carbon which has four different groups around itself, then that carbon is called a stereocenter or asymmetric carbon, because all the four groups are different. It's called asymmetric carbon. So obviously the resulting molecule would lack symmetry and is referred to as asymmetric molecule. The asymmetry of molecule is actually responsible for the optical activity in such organic compounds. A new term again, chirality. The objects which are non-superimposable on their mirror images are said to be chiral, and this property is called chirality. Let's look at a simple example. Take your hand, place it in a mirror, and you take the mirror image and superimpose that, that is, place that mirror image on your other hand. Are they the same? Are they identical? No. So hand, that is a pair of hands, or an example of non-superimposable mirror images. Similarly, your feet. However, we have seen many things that are superimposable on the mirror image. So what are they called? Some of you might have guessed by now. And yes, it is archival. So what is archival? Objects which have objects which have superimposable mirror images are called archival. For example, these two on my right. So these are called archival, or even sometimes they are called as non-archival objects. So let's illustrate this using a chemical molecule, organic chemical molecule. So let us consider two simple molecules, propan-2-ol and butan-2-ol, and their mirror images. First, we will be looking at propan-2-ol. So this is propan-2-ol in the left, and the one in the middle, that is called B, is the mirror image of A. And I am rotating B by 180 degrees and I get C. C is obtained by rotating B by 180 degrees. C is superimposable on its mirror image A. So, since propan-2-ol does not contain a asymmetric carbon, as all the four groups attached to the tetrahedral carbon are not different, this is called archival molecule. We call it archival because the mirror images are superimposable, and this on my left, that is, it lacks a stereocenter, is an observation for archival molecule. Now let's take butan-2-ol. We have butan-2-ol. I take a molecule D, that is on my left of the screen, and I place it in front of a mirror. I get the molecule in E, that is mirror image of D. Now I rotate E by 180 degrees, and that is F. F is obtained by rotating E by 180 degrees, but F is non-superimposable on its mirror image D. Yeah? So what do you observe over here? Butan-2-ol has four different groups attached to tetrahedral carbon, and as expected is chiral. So what can you conclude from the last two slides? For carbon which is chiral, it has a stereocenter, that is an asymmetric carbon, which means that the groups around carbon, all the four groups are different. However, in case of archival compound, we saw that not all the four groups are different. So this is the conclusion. Propan-2-ol is archival and butan-2-ol is chiral. And some common examples of chiral molecules are given here. Example 2-chlorobutane, etc. So till now we are seeing what is optical isomerism. For that we saw what is plane polarized light and what is dextro and levorotatory. Then we saw what is a stereocenter, that is an asymmetric carbon. Then we saw about chirality, that is non-superimposable mirror images. Then we saw an illustration of propan-2-ol and butan-2-ol. We saw that propan-2-ol is archival because it lacks four different groups around the carbon, that is, not all the four groups around that carbon is different. And in case of butan-2-ol, we saw that all the four groups around that carbon is different, and so we called it as asymmetric carbon, that is, it's a stereocenter, and we saw that it is chiral. So that was a summary till now. Now let's look at something called enantiomers. The stereoisomers related to each other as non-superimposable mirror images are called enantiomers. So what are stereoisomers? Stereoisomers are those isomers that differ in the spatial arrangement of atoms or groups around a carbon. So the stereoisomers related to each other as non-superimposable mirror images are called enantiomers. Enantiomers possess identical physical properties. For example, melting point, boiling points, refractive index, all these are same given two enantiomers. They only differ with respect to the rotation of plane polarized light. That is, if one of them is dextrorotatory, the other one will be levorotatory. That is, in simple words, if one of the compound rotates, the plane polarized light, say by plus 5 degrees, and the other compound, which is the enantiomer of the previous compound, will rotate the plane polarized light by minus 5 degrees. Quite simple, right? So let's move on to something we have heard before. We have seen this in the first slide, that is racemic mixture. So what's a racemic mixture? A mixture containing two enantiomers in equal proportions will have zero optical rotation. Quite intuitive, right? I take a compound that rotates a plane polarized light, say by 5 degrees, plus 5 degrees, and I take its enantiomer, and so the enantiomer will rotate the plane polarized light by minus 5 degrees. So I mix them in equal proportions. Then obviously the rotations will get cancelled, right? That's the reason why racemic mixture has zero optical rotation, as the rotation due to one isomer will be cancelled by the rotation due to other isomer. Such a mixture is known as racemic mixture or racemic modification, and a racemic mixture is represented by prefixing DL or plus minus before the name. Example, plus minus butane 2-ol. So if I say it as plus minus butane 2-ol, it's a racemic mixture of plus and minus butane 2-ol. And the optical rotation of plus minus butane 2-ol is 0 because of cancelling of the rotation by individual isomers. The process of conversion of an enantiomer into a racemic mixture is known as racemization. Retention. Retention of configuration is the preservation of integrity of spatial arrangement of bonds in an asymmetric center during a chemical reaction or transformation. In simple words, if you take a compound having a spatial arrangement and a carbon having 4 different groups around it, then after the reaction, if the spatial integrity, that is the relative orientation of all the groups, are preserved, then the compound is said to have retention in its configuration after the chemical reaction. It is also the configurational orientation when a chemical species, say XCABC, is converted into the chemical species YCABC, having the same relative configuration. So I have taken the compound ACXB and I treat it with Y. After the reaction, I get ACYB, the same order around that carbon. So this is called retention of configuration after the chemical reaction. The relative ordering of all the groups is preserved. In general, if during a reaction no bond to the stereocenter is broken, the product will have the same general configuration of groups around the stereocenter as that of the reactant. Such a reaction is said to proceed with retention of configuration. Example, the reaction that takes place when minus 2-methyl-butane 1-ol is heated with concentrated hydrochloric acid. Also observe that a carbon-bearing OH group has 2 hydrogen atoms and the carbon is symmetric. Now let's look at the outcomes of a reaction, by which I mean that I take a substrate and I make it undergo a chemical reaction. Then we will be looking at the stereochemistry of the product formed. There are 3 outcomes for a reaction of an asymmetric carbon atom. Consider the replacement of a group X by Y in the following reaction. So we have this substrate in the middle. I make it undergo a reaction by treating it with Y. Then there are 3 possible cases. I can get A or B or a mixture of A and B. If A is the only compound formed, then the process is called retention of configuration. Observe that the spatial integrity is preserved in A. However, if B is the only product formed, then the process is called inversion of configuration. This is what happens in SN2 reaction, and we will see why that happens soon. So what has happened? The spatial integrity is reversed. The relative orientation of all the groups have been reversed. So that's called inversion. If a 50:50 mixture of about two compounds is obtained, then the process is called racemation. Why? A and B are enantiomers. And if I get equimolar concentration of A and B, then it's called a racemic mixture. And hence the process is called racemation. That's what is given over here. And in such a case, the product A plus B is optically inactive. Why? We have seen that before, because one isomer will rotate the light to the left, then the other will rotate to the right. That is, the two isomers will rotate the light in opposite directions, and since we have equimolar concentration, the optical activity will be cancelled. And this phenomenon is termed as external compensation. Why external? The optical activity is cancelled by two different compounds, not by a single compound itself. So it's called external compensation. So now let's see what exactly happens in an SN2 reaction. Why do we get an inversion in configuration? In case of optically active alkyl halide, the product formed as a result of SN2 mechanism has an inverted configuration as compared to the reactant. This is what I've told in the beginning of the video, and I'm telling it again, and now we will be seeing why. This is because the nucleophile attaches itself on the side opposite to the one where the halogen atom is present. So if I have -2 bromo-octane and I make it react with sodium hydroxide, you expect a nucleophilic substitution, and now we have seen that we will be getting plus octane 2-ol, that is an inversion in configuration. So why is there an inversion? It's very important to understand that the nucleophile approaches and attacks the carbon from the side opposite to that side where halogen is present. So yeah, the configuration gets inverted because of this other side attack. So this is the reaction, and you see that the spatial orientation of each groups has been inverted, so we call it inversion. Now let's look at outcomes of an SN1 reaction. We should be expecting a racemic mixture. Yeah, so let's move on. In case of optically active alkyl halide, this is important. The reactant should itself be optically active in first place, otherwise there's no point in discussing stereochemistry. In case of optically active alkyl halides, SN1 reactions are accompanied by racemation. Actually, the carbocation formed in the slow step being sp2 hybridized is planar. So carbocation sp2 hybridized planar, and hence it is achiral. The attack of the nucleophile may be accomplished from either side, resulting in a mixture of compounds, one having the same configuration, the OH attaching on the same position as halide ion, and the other having opposite configuration, the OH attaching on the side opposite to halide ion. So what is the main thing over here? We get a carbocation intermediate in SN1 reaction. Carbocation is sp2 hybridized, it is planar, so the attack can happen in any side, from any side, and the probability of attack is equal. It can happen from any side with equal probability. So there's an equimolar mixture of a compound with retention and a compound with inverted configuration, and hence it is called racemic mixture, and the optical activity is 0 because of external compensation. This may be illustrated by hydrolysis of optically active 2-bromobutane. 2-bromobutane hydrolysis is SN1 because the solvent is polar protic. So it results in formation of plus minus butane 2-ol. So this is the reaction mechanism. What happens exactly? We get a carbocation, it is planar, the attack happens from any side, and we get inversion and retention of configuration, both of these in equal concentration, and hence we get a racemic mixture. I hope things are clear now. In SN1 we get a racemic mixture, in SN2 we get a inversion of configuration. So we have seen SN1 and SN2 now. Let's try to compare both of these. Okay, we compare SN1 and SN2 reaction. Rate law. SN1 is unimolecular and SN2 is bimolecular. Haloalkane reactivity. So SN1 tertiary is most and primary is least. In SN2 primary is most and tertiary is least reactive. Solvent. SN1 requires a polar protic solvent. However, for SN2 we expect a polar aprotic solvent. Nucleophile. A weak nucleophile and a strong nucleophile is required in SN2. Stereochemistry. This we have seen in detail in this video. SN1 is racemic mixture, SN2 is inversion. And for these two to happen, the substrate should initially be optically active. Otherwise, there is no point in discussing the stereochemistry of the products. The products itself will be inactive because there is no asymmetric carbon. So with this, I would like to conclude this video. In this video, we saw in detail the stereochemical aspects of nucleophilic substitution reaction. We saw that in SN1 there is a racemic mixture and SN2 results in inversion if the reactant is optically active. In the next video, I will be talking about reaction of haloarenes. I hope the content in this video was clear. It is pretty important to understand stereochemistry at this level, and I hope to see you in the next video. Goodbye.